What's going on, linear algebros? It's Mr. C here, and in this video I'm going to show you how to find a cross product of two vectors from 3 space, which of course you can only cross product two vectors if they come from 3 space.
Come on now, dog. Come on, man.
Alright, the two vectors we're going to cross product, we got the vector u with components 3, 2, and -1, and we also have the vector v having components 0, 2, and -3.
Lord have mercy.
And in this video, I'm going to show you how to find the cross product vector using the Rule of Sarrus. By the way, do you know what you call a king dinosaur? Or a Rule of Sarrus?
Oh, brother, this guy stinks!
I know. Give me the buzzer.
Oh, sorry.
Anyway, to set this up, let's go ahead and form a 3x3 determinant. Remember, it's just the vertical bars, no brackets.
Stop it.
And in the first row, I'll put the vectors I, j, and k. I don't always tell vector jokes, but when I do, I, j, k. And since we're trying to find the cross product of u cross v, we're going to put the components of u in the second row, 3, 2, -1, and the components of v in the third row, 0, 2, and -3.
Bruh.
Now recall, with the Rule of Sarrus, you have to generate two additional columns to the right of the determinant bars, and those two columns are going to be columns 1 and 2. So let's jot down I and j over to the right. Then underneath that, the entries 3 and 2, and underneath those, the entries 0 and 2.
We must stay focused, brothers.
So you might remember that we have to form some diagonals, and that's the whole point of putting these additional two columns here. And we're going to have some diagonals going down and to the right. And those diagonals are going to come from, well, starting with the first entry in row 1. We're going to take the vector I and multiply it to these other diagonal entries, 2 and -3. That's going to give us -6i.
Affirmative.
We're going to add that to another product of entries along a diagonal. That would be plus 0j. There we go. And then we'll move over to the next column, and we're going to take k and multiply it to the entries of 3 and 2. So that'll be plus 6k. Alright, we also have to multiply entries along the diagonals that go down and to the left. And we'll use the first diagonal starting with this very last entry here in row 1, j, and that's going to get multiplied to 3 and -3. So that'll give us -9j. We'll add that to this product, where we'll take I, multiply it to -1 and 2, so plus -2i. And then we'll multiply k times 2 and 0, so plus 0k. Now, of course, if you want to simplify these expressions, feel free to do so. We'll have -6i plus 6k for those diagonals. And then down here, we're going to have -2i minus 9j. Alright, so for the actual cross product vector,
I'm going to do what's called a pro gamer move.
what we're going to do is we're going to take this expression, so coming from the diagonals going down and to the right, and from that we'll subtract this expression, which come from the diagonals going down and to the left. So let's jot that down. So we'll have -6i plus 6k minus -2i
Negative.
minus 9j. And then just let the good old algebra skills kick in here, where we'll distribute this minus sign,
Negative.
clear the brackets. We can unleash the first set of brackets, so -6i plus 6k plus 2i plus 9j. And then combining like terms, we're going to have -4i plus 9j plus 6k. And this right here would be our cross product vector. Of course, it's expressed in the format I, j, and k, which you can convert this back to component form by writing out an ordered triple, where the first component is going to be -4, second component 9, and third component 6. Both of these represent the same vector, they're just expressed in different notations. And there it is. That's our cross product vector using the Rule of Sarrus. One more thing that I want to mention before I let you guys go is that of the concept of a cross product vector.
Emotional, damn it!
So let's imagine that we have the two vectors u and v lying in a plane. We'll just be very generic with my diagram here. That's a vector u, and this is a vector v. When we form the cross product of these two vectors, you end up forming a vector that is perpendicular to both of them. So you would have this vector poking out of the plane like so. That would be our cross product vector u cross v. Now, of course, it could point in the other direction, still poking out of the plane, but facing down. And your choice of direction will actually be based on something called the right-hand rule, which I'll discuss at a later time. But again, I just want to note that the cross product vector here is perpendicular to both the vectors u and the vector v, and obviously it's also perpendicular to the plane itself. Alright, so that's the last thing I wanted to mention. Of course, if you have any questions, let me know. Otherwise, thanks for watching this demonstration on finding the cross product vector using the Rule of Sarrus, and I'll catch you guys in the next video. Keep bossing up, linear algebros.
Pause.